All right, welcome to our last video here of section 3.2. We're going to look at symmetry. Symmetry means that you can flip or turn the graph and it will appear to look exactly the same. So our symmetry test was going to be with respect to the x-axis, meaning we're going to flip it over the x-axis. We're going to flip it up and down. And if it looks the same, then it's symmetrical to the x-axis. The y-axis, we're flipping it over the y-axis left and right. And it's symmetrical to the origin means you're going to spin the graph. And we're going to turn it until it looks the same again. So we're not going to always be able to graph the equations that we encounter because they're going to be just too difficult to enter into the calculator to get a picture. So we're going to do this more algebraically. So to find symmetry with the x-axis, what you're going to do is everywhere in the equation you see the variable y, you're going to replace it with negative y in parentheses in case it's squared. All right. And then you're going to simplify the new equation, and if it comes right back to the original same equation, then that graph is symmetrical to the x-axis. It's a mirror image if you flip it over the x-axis. For the y-axis, because we're just changing the name from x to y, then in my definition you should change the y's to the x's. So now you replace the x with a negative x, again, in parentheses everywhere in the equation. Every place there's an x, you put parentheses around it and put in a negative x. Simplify it again, and if you come back to the original same equation, then the graph is symmetrical to the y-axis. It's being flipped over the y-axis. And the origin, to be symmetrical to the origin, you have to do both the x and the y rule. You got to take all the x's and make them negative x's, and take all the y's and make them negative y's. And if you can simplify the equation to come back to the same equation, then the graph is symmetrical to the origin, which means you're basically putting your pencil at the origin and turning your paper 180 degrees, and it looks exactly the same if you actually saw the graph. Okay? Now, again, a quick reference. Notice that nowhere in the directions does it say function. It always says an equation. So we don't want to see f of x or g of x. If you do, you got to take those out and replace them with y in case you got to put in a negative y. All right? Okay. Hold on. Wait a minute. If we put in a negative y and we want to see the equation be the same, then wouldn't your y's have to be raised to an even power, and that would cancel out the negative? And the same thing for the negative x. So the only way that symmetry is going to work for x and y, you need to see your x's and y's raised to even powers. That sounds good there. But that doesn't necessarily have to work for the origin. So that one's going to be kind of sneaky. All right, so let's look at some examples. Here's my equation. Again, I'm going to keep these short and sweet so we don't have to do that much substitution. So y is equal to x squared. That's my equation. Now it says, find the symmetry. Well, let's be smart about this. If I tried to test this for the x-axis, and if I put a negative y right here, it's now going to be negative y equals positive x squared. It's not the same equation. If I divide the negative off the y over to the x squared, then it's y equals negative x squared. Not the same. So when I test for x-axis and y-axis, I'm going to use some knowledge about my even powers. That if I see an x being squared, then that's where I want to put my negative x. So I'm going to test for the y-axis symmetry. So I'm putting in a negative x here for the x. Remember, parentheses around my x, put in the negative x. I square a negative x, I'm back to x squared. It's the same equation. So this is symmetrical to the y-axis. So again, remember, if you put in a negative x, you're flipping it over the other variable y. If I put in a negative y, I'm flipping it over the other variable x. If I make both variables negative, then we're turning. It's the origin. All right, next example, x equals y to the fourth. Again, even power on the y. I probably want to put in a negative y, so we're testing the x-axis. So negative y raised to the fourth power. Okay, that's back to y to the fourth. This is symmetrical to the x-axis. So far, so good. X squared plus y squared equals 9. Okay, wait a minute. Both powers are even. So I think we're going to get all these to work. If I put in a negative x, I get x squared plus y squared equals 9 again. So symmetrical to the y-axis. If I put in a negative y, I come back to x squared plus y squared equals 9, symmetrical to the x-axis. And for the origin, well, I mean, wait a minute. I mean, if I got both of these to work, if negative x being squared comes back to x squared and negative y being squared comes back to y squared, if I put them both in, then I should come back to the original. So if both y-axis and x-axis symmetry works, then this has to be symmetrical to the origin. Okay? So I don't have to test the origin if both the x-axis and y-axis symmetry test work. All right, they both work, then the origin test will also work. It will be symmetrical to the origin. Now be careful. It doesn't work in reverse. So what I mean by that is that if you test for symmetrical about the origin, you can't say, well, then it's got to be symmetrical to the y-axis and the x-axis as well. No, you test the two individual axes first. If they both work, then the origin also works. Here's an example of what I'm talking about. Y equals x to the third power. There's no even powers here. So it wouldn't be beneficial to put in a negative y only. I can't get back to the same equation. I put in a negative x. That's going to be negative times a negative times a negative. That's a negative x cubed. I'm not back to the original equation. But I can do an origin test. Let's put in a negative for the y and a negative for the x. So if you see odd powers only, then only test the origin. Now watch what happens here. This will stay negative y. This is going to be negative x cubed. Well, wait a minute. That's not the original equation. Right, but how do I change this negative y back to a positive y? Is I divide both sides by technically a negative 1 is in front of my y. Well, negative divided by a negative is a positive. Negative divided by a negative is a positive. I'm back to the original equation. That is symmetrical to the origin. Only. All right? So even powers, test individual x, individual y. If both x squared and y, x is squared, y is squared, or both x and y raised to even powers, it will be all three. If I got all odd powers, origin only. All right? So there's my test for symmetry. Now, one important concept here I want you to put about symmetrical to the x-axis. If I can flip it over the x-axis and it looks exactly the same, that's not a function. That's not a function. It's not going to pass the vertical line test. So remember that one, x-axis, that was right here, symmetrical to the x-axis. Remember we said this equation has y to an even power. This is not a function. So functions will never be symmetrical to the x-axis. Never x-axis for functions. Equations, yes, because those are relations. Functions, no. All right. And that finishes up our video for section 3.2.